Information theory gives us the fundamental framework for measuring exactly how much information is contained within a signal or a data set. At the very core of this framework is a concept called entropy. Invented by mathematician Shannon, entropy acts as the primary engine for modern machine learning, powering the decision-making processes of algorithms like decision trees and the logic behind large language models. To really grasp how AI makes these decisions, we first need to understand how it measures uncertainty. Let's think about this using a surprise analogy with sports. In a cricket match between a world-class team like India and a much lower-ranked team like Maldives, the outcome is highly predictable. Because we practically know the result beforehand, there is almost zero uncertainty. In this highly predictable scenario, entropy is very low. Now contrast that with a World Cup final between two powerhouses like India and Australia. This is a true 50-50 situation. The outcome is completely uncertain and the suspense is absolute. This represents maximum entropy. There's also a middle ground. Take a match like India versus Nepal. India is highly likely to win, but there is always that small lingering chance for an upset. This scenario gives us medium entropy. The relationship here is direct and steady. The more unpredictable an outcome is, the higher the entropy. Conversely, the more certain you are of an outcome, the lower the entropy. So how do we actually measure this surprise mathematically? Let's look at Shannon's formula for entropy right here. Let's break it down piece by piece. First, this term represents the probability of a specific outcome happening. Next to it, we use a log-based operation which essentially converts these probabilities into units called bits. This is how we measure our surprise. Now, because the logarithm of a fractional probability is always a negative number, a minus sign is placed at the very beginning of the formula. This simply flips the result, so our final entropy value is positive. Finally, this sigma symbol tells us to sum up all these calculations for every single possible outcome in our scenario. If one particular outcome is almost perfectly certain, the sum of all this will drop down near zero. But if every outcome is equally likely, the sum will be large, reflecting that higher uncertainty. Let's see this math in action with a few stepped examples. First, we calculate the entropy for a perfectly fair coin. The probability of getting heads is 0.5 and tails is 0.5. When we plug 0.5 into our formula for both sides and add them together, we get a clean result of 1.0 bits. This is maximum entropy because we have absolutely no idea what is coming next. Next, let's look at a rigged coin. Here the probability of heads is heavily skewed to 0.99, leaving tails at just 0.01. When we run the math, because one outcome is so overwhelmingly likely, our surprise level drops significantly to about 0.08 bits. This is very low entropy since we almost always know it will land on heads. Finally, consider a loaded die that always, without fail, rolls a 6. The probability of rolling a 6 is 1.0 and all other outcomes are precisely 0. When we calculate this, it yields an entropy of absolutely 0. There is perfect certainty and zero surprise. The core takeaway to remember is this. Entropy is 1.0 when we are totally uncertain, and it scales all the way down to 0 when we are totally certain. As we move forward, we'll see how models like decision trees use this exact measurement of uncertainty to determine which questions yield the most information gain.
How do decision trees know which questions are actually worth asking? The entire process is driven by a metric called information gain, which you can see right here. It is simply calculated by taking the entropy or uncertainty before asking a question and subtracting the entropy after asking that question. The golden rule is simple. A higher information gain means you found a better, more informative question to split your data on. Let's look at a practical example of this applied to a loan approval process. We start with 10 customers. 5 are approved and 5 are rejected. Because this is an exact 50-50 split, our starting entropy is at its absolute maximum, which is 1.0. We are perfectly uncertain. Now, we have two possible questions to ask. If we ask question A, does the customer own a home? Look at what happens. The data splits into two groups that are mostly approved or mostly rejected. Because these new groups are less mixed, the resulting entropy is low, meaning our information gain is high. On the other hand, what if we ask question B about the length of the customer's name? Well, the resulting groups remain just as mixed as before. The entropy stays high and our information gain is low. Given this math, the decision tree will naturally choose question A because it actually helps us make a decision. This same concept of measuring uncertainty is crucial for modern AI models like ChatGPT, but they use a variation. Cross-entropy serves as the learning mechanism, acting as a mistake score or loss function. If the model is predicting the next word and predicts bank with 90% confidence when the actual answer is indeed bank, the cross-entropy loss is very low. It receives a small penalty. But if it makes a bad prediction and misses the actual answer, the loss skyrockets, resulting in a large penalty. During training, the AI's primary goal is to minimize this cross-entropy loss, to improve its accuracy. To really ground this idea, let's look at the spectrum of entropy at the bottom left. On the far left, we have zero entropy, which represents total certainty, like the fact that it always rains in Cherrapunji. The middle shows medium entropy, where there is some uncertainty, much like a typical Mumbai monsoon. Finally, on the far right, we have max entropy, which represents total chaos, where outcomes are a 50-50 mix, just like flipping a coin. Now let's tie it all together with the full math of a decision tree split. We begin again with 10 loan applications sitting at an entropy of 1.0. By asking our best question, is their income greater than 50K, the tree branches out. The yes branch drops down to an entropy of 0.47 and the no branch drops to 0.54. Both of these branches are much cleaner than the original state. To find out exactly how much we learnt, we take the original entropy of 1.0 and subtract the average of our new branches. This gives us an information gain of 0.495, which is fantastic. Here is the core takeaway. Entropy is just a mathematical measure of messiness, and information gain is how much we clean up that mess with a single good question. Now that we understand how these mathematical splits work on a single level, let's see how these principles are applied in massive real-world systems like healthcare diagnostics and email filtering.
In healthcare systems at places like Apollo hospitals, diagnostic systems use entropy-based trees for patient triage. When a patient arrives, the initial state is chest pain. At this stage, the starting entropy is very high because there are several possible causes, which you can see branching out below, like a heart attack, anxiety, or acid reflux. The AI asks questions that provide the highest information gain first, such as asking if the pain radiates to the left arm. Each answer drops the entropy significantly, filtering out the noise until a diagnosis is reached with nearly zero entropy. Similarly, Gmail uses these exact principles for spam detection. Looking at the information gain ranking table, we see features ranked by how much uncertainty they remove. The question asking if the subject contains free money is an excellent predictor. It has a high information gain of 0.42, ranking it number 1. However, down at the bottom, the question asking if the email contains the word the has a tiny gain of 0.001. Because the word the appears equally in almost all emails, spam or not, it reduces almost zero uncertainty. It is completely ignored by the AI. Now let's look at the underlying math in the code section. The first block demonstrates how to build an entropy calculator from scratch. The function calculateEntropy implements Shannon's formula. It initializes entropy at 0 and loops through a list of probabilities. For each probability, it subtracts p times the log base 2 of p from the total. Testing this function reveals that a scenario with only one possible outcome results in pure certainty, or 0 bits of entropy. A fair coin flip, however, results in 1 bit, representing maximum uncertainty for 2 outcomes. This behavior is beautifully visualized in the binary entropy graph. Notice this hill-shaped graph. Entropy is lowest at the edges where probability is near 0 or near 1. It reaches its absolute peak of 1.0 exactly at the center where the probability is 0.5. This perfectly visualizes how uncertainty is maximized when outcomes are equally likely.
Moving over to information gain calculation, we see it defined as the parent entropy minus the weighted entropy of the subgroups after the split. In the loan approval example below, checking if income is greater than 50,000 yields high gain because it creates pure groups. Conversely, checking if the name starts with A shows no improvement and has zero gain. The final code snippet shows how to implement this using a real library. We build a decision tree classifier and explicitly set the criteria to entropy. After training, the model outputs a feature importance chart, ranking variables like credit score by how much they reduced entropy. Below that, it generates a visualization of the resulting tree showing the exact entropy values at every branching node. To test this practically, look at the bottom section. If a classification system has a 70-20-10 split, the entropy is relatively low because one class dominates. But a 33-33-33 split maximizes entropy across three categories. Also, in the information gain comparison, a question that creates mixed groups has lower gain than one that creates smaller but purer groups. Finally, by applying this to a Hotstar recommendation engine, you can use entropy to find the strongest predictor of whether a user will finish a show. Ultimately, entropy measures uncertainty, and information gain measures how much a question reduces that uncertainty, allowing AI to automatically find the most important signals in any dataset.